Okay, so let's start. Thank you all for coming. Well, it's a pleasure to introduce our speaker today. It's Professor Edgar Knobloch from University of California, Berkeley. It's a pleasure to me to introduce Edgar. Is well, some of you know him. He's been a long-time collaborator of myself and here at the FISC. And well, what to say, he is an expert on non-linear dynamics of dissipative system, fluid dynamics, pattern formation, and he is our preferred world expert. No? So when we have new problem or something, we always address to him for his advice, because he's always give a very good insight. So well, I'll not say he has a large number of papers that you can check. Is no need for introduction in that sense. So I'll let him the floor to him through this talk. He'll talk about one of the things he works on, which is fluid dynamics or problems on turbulence. Okay, and this so please, Edgar, go ahead.
Okay, thank you, Damia, for the introduction, and it's of course a great pleasure to be back in Palma after 4 years and some interruptions due to COVID. So I'm going to talk today about instability-driven turbulence. So this is work done most recently with my postdoc, Adrian van Kan, but also with the able assistance of Benjamin Favier from Marseille and Keith Julian in Boulder, Colorado. So this talk will be divided into two parts. The first part will be about two-dimensional flows, two-dimensional turbulence. And then the second half, I want to relate what we learned from the two-dimensional problem to what happens in three-dimensional systems, three-dimensional turbulence, but not fully three-dimensional. So anisotropic, but three-dimensional turbulence. So let me start with some motivation. So in my group, we are interested in geophysical flows. And in particular, we're interested in the generation of large-scale structures, like vortices, hurricanes, for example. Also, the atmospheric jet that you can see there in the picture on the top right. So these are coherent structures that live in the background of turbulence, typically, because the Reynolds numbers are extremely large. And one of the things we're interested in this kind of self-organized turbulent flows, and I'll say more about that. These things also occur in the solar system, and you might have seen pictures of the polar region of Saturn with this nice hexagonal structure that rotates and has these embedded vortices within it. The Juno mission that recently sent us pictures from Jupiter shows similar structures in the polar regions of Jupiter with this pentagonal vortex structure, which is also long-lived. And of course, Jupiter is well known for supporting long-lived vortices, like the red spot, the famous red spot that has attracted interest all the way back to Galileo, I guess. But we're also interested in these kinds of flows from more microscopic perspective, and that has to do with the turbulence in active systems. By active systems, I mean systems of particles, which, for example, burn energy and translate that energy into self-propelled motion. And there are interesting similarities between the flows at very large Reynolds numbers, the ones at the top, and some of the flows that you see at low Reynolds numbers. Down here, you get this same kind of streaming and self-organized flow. For example, in this microtubule kinesin suspension, or in a suspension of swimming sperm. And in some cases, you see in experiments that the system can essentially crystallize into a state of relatively well-organized vortices. And we'll talk about that also. Now, the important thing for our purposes is that we're going to be dealing with, in experiments certainly, we're going to be dealing with thin structures. And we're going to try to approximate the thin structures by purely two-dimensional structures, but then we'll try to, include the third direction, but not in a fully isotropic way, okay? And so this is just motivated by this picture of sunrise over the Earth from one of the Apollo missions. You can see that the Earth's atmosphere is a very thin layer relative to the radius of the Earth. And so we're interested in studying turbulence in thin layers of that type. Now, in many cases, the turbulence in such layers is generated by instabilities. These could be shear flow instabilities, like this Kelvin-Helmholtz wave, which I guess is probably in Boulder, Colorado. It's very famous for having these nice pictures. Or it can be generated by turbulent convection, such as arises, for example, in cumulus clouds. But you also see some similar structures at much smaller scales, like in the active systems that I mentioned. So we're going to be talking about 2D turbulence driven by instabilities. And this is different from what most people do, because what most people do is they might put some random force to stir the teacup and try to understand what is the property of the resulting flow. Now, those formulations, of course, are very useful. They led to the well-known Kolmogorov theory, for example, but they have a force that is constant, is preserved in time. It doesn't respond to the turbulent state that is generated by that force. Whereas if you have instability force turbulence, the state that is generated by the forcing can react back on the forcing, right? And so we're interested in trying to understand what is the effect of this back reaction on the forcing. So let me say a few words about 2D turbulence, because I'm not sure everybody here knows about 2D turbulence. So the idea with 2D turbulence is that you're going to force the system at some small scale, described by this small L. And then in 2 dimensions, there's a well-known so-called inverse energy cascade that transports energy from the scale that is forced to larger and larger scales. And that's a process that's been called the spectral condensation. That's a word that goes back to the work of Bob Krechner. So this inverse cascade is characteristic of 2 dimensions. In fully 3-dimensional turbulence, of course, the turbulence cascades in the normal way from the scales at which you're forcing the system towards smaller scales until it's dissipated at the viscous scale. Okay, so that's a big difference. And if you do simulations, you find that a 2D turbulent flow driven by random forcing organizes into these large-scale vortices, which is an example of this spectral condensation process I mentioned. Now, what is the problem that we actually study? Well, here is the Navier-Stokes equation. It's a little bit different from what you might be used to seeing. So first of all, we include hyperviscosity in the flow, and that's simply to get a larger range of resolved scales than you can get with normal viscosity. That's a normal procedure. It doesn't affect anything pretty much. We have a nonlinear term that we introduce, which is analogous to a term that appears, for example, in some of the hydrodynamic models of swarming. For example, the Toner 2 model has a term of that type. We include this term because the spectral condensation process, it takes energy from the force scales to larger and larger scales, and it's very hard to get a stationary state as a function of time, because energy keeps piling up at the box scale of your numerical computation. And this nonlinear term actually saturates that process and allows you to study the statistical properties of the stationary state that is generated by this process. The important thing for our purposes is the last term. That's the forcing term. And the forcing term we write in the following way. So we have the forcing term. It's going to depend on a parameter gamma, and it's going to be driven partly by just a random force. That's the classical situation, and an instability contribution whose importance is measured by this parameter gamma. So the way we model the instability is through this linear operator L. Notice it depends on the state of the system U, and it's best to think about that in Fourier space. So in Fourier space, what we do is we have a growth rate which depends on the wave number This growth rate is positive in a certain annulus in wave number space. And the annulus is between K1 and K2. So I have a certain annulus in wave number space that I'm forcing. And this is typically what happens with hydrodynamic instabilities, of course, because hydrodynamic instabilities have a characteristic scale. And then because of nonlinear effects, there are some other modes nearby that are also excited, but you're not forcing all the scales at the same time. Yeah. Yeah, so the important thing is that the forcing term depends on the state of the system U, right? That is not the case for the random force, right? And so depending on what state you have, you're going to get different forcing, because the forcing depends on the Fourier transform of U. Sorry? Well, it's because what we're doing essentially, we're going to do, you can think of it as a homotopic continuation from purely randomly forced system to a purely instability force system. Okay, so we're just going to vary gamma as a free parameter. You know, when gamma is 0, you're in the classical situation where everything is driven by random forcing. When gamma is 1, the random forcing is absent, and all of the forcing is confined to this to this instability-driven mechanism. Okay, so it's just a way of extrapolating between these two possibilities. Yeah. You can think of this as a model of, you know, this could be from shear flow instability. It could be from convective instability in the third dimension, something like that. It's just a model of a. You could. Yeah. Yeah. For instance. Yeah. Well, we'll talk about Rayleigh-Benard instability in 3 dimensions, if you allow me to get to that, because we'll try to compare what you learn from this with what actually happens in 3 dimensions. Okay. It's a model. It's a model, but the important thing is that the forcing depends on the state of the system. Yeah. 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 Okay, so that's the model that we have, and so we're going to vary the parameter lambda. And so before I do that, let me just tell you a little bit about the parameters. So K1 is chosen to be 33, K2, the larger wave number, is 40. So that determines this annulus in wave number space that is being forced. Hyperviscosity is of order 4. We non-dimensionalize relative to the RMS velocity. The largest scale L1 is 2 pi over K1, of course. That's from the forcing band. We have an advective time. And if we non-dimensionalize the problem, you generate 2 Reynolds numbers. There's the classical Reynolds number that determines the importance of the advective term relative to viscosity. And that's going to be high in the simulations. And then we have a new Reynolds number associated with that nonlinear term, which is also going to be large in the problem. But this one will be fixed. This one will vary. We do the calculations are typically done on a 512 by 512 grid. But because of the slow process of energy transfer from the 4 scales to large scales, if you want to get a statistically stationary state, you may have to integrate for a very long time. So here are some of the things that you find in this model. So So when gamma is 0, so there's no instability forcing, everything is driven by just random stirring, you find this condensation process that I've already described, and you saw a picture of that. As I increase the contribution from the instability forcing, you find these small-scale vortices appearing inside these condensates, as you can see over here. The scale of these structures is something like twice the scale at which you're forcing the system, that scale L1. And the sign of the small vortices that appear in these condensates correlates with the ambient vorticity. So these are vorticity plots, by the way, since you're familiar with vorticity plots. And then as you increase gamma some more, you find that the condensate breaks down and releases these small-scale vortices, and you get a gas of these kinds of structures that are moving around. I'll show you a movie of this in just a second. And then you can take this state, allow it to evolve into a stationary state, and then you can gradually decrease gamma back to small values, and you find that this gas actually crystallizes into this kind of vortex lattice. And I'll show you some pictures of that. So let me show you, So let me show you a movie of some of this. So this starts with random initial conditions. I'm not going to show you the whole movie, but I want to just show you first the formation of these vortices. You notice you have vortices, these kind of tripolar structures of both signs, but eventually one or other of these signs wins, and you get a vortex lattice composed of vortices of just one sign, either positive or negative. So you have actually a phase transition, a non-equilibrium phase transition in the system that generates structures of just a single sign. And you can kind of see some of the processes. You know, if I go over here, you can see now that the structures with the blue center are dominant. Occasionally, you see one with the red center, but you know that collides very quickly with some of the other ones and is disrupted. And eventually, you end up with a gas of vortices of just a single sign. Now you can look at this in terms of the spectra. This is something that is done conventionally in turbulence theory. So this is the kinetic energy spectrum, and you can see that when gamma is 0, so I'm purely forcing by this random forcing, you get the classical Kolmogorov spectrum. This is the inverse energy cascade I talked about. Up here, you have a k⁻³ spectrum that's due to the large-scale vortices. Now, as you increase gamma, the shape of the spectrum changes dramatically, and you get a peak roughly twice the forcing scale, and then you're suppressing, as you can see, the ability of this condensate to form. So you have a very dramatic effect on the spectrum as you vary this gamma parameter. You can also think about this in terms of the fluxes of energy. So here is the flux of energy as a function of the wave number. Here is the forcing band, and you can see that when gamma is 0, you have a large negative flux. That's the inverse energy cascade. And then, of course, you have some cascades towards viscous scales. If you make gamma equal to 1, so it's purely instability force, this inverse cascade is shut off, and you get a transport just to nearby scales near to the forcing scales. You can also look at the entropy flux. Entropy is the integral of the square of the vorticity. And you can see that the entropy flux is entirely positive when gamma is equal to 0, so random forcing. This gives you the entropy cascade, k⁻³. It's a direct cascade. When you turn the instability forcing, you get some entropy leakage upscale. So here's a summary of the regime diagram. So we're plotting the entropy as a function of that parameter gamma I introduced in the forcing. When gamma is 0, you get this condensate state that I mentioned already. Then this gives way to this kind of mixed state with small scale vortices embedded in the large scale structure. There's hysteresis there. And then finally, this kind of envelope that collects all these small scale vortices breaks down, and you get a state without the large scale structures, which I'm calling a vortex gas. That last state is actually a transient state. If you look at it in more detail for longer times, and these are very long times, for example, when gamma is 1, you have a kind of pause here, and then you get a nucleation of lots of these vortices, all of the same sign, and then you end up with a dense gas that looks something like this here at the bottom right. If you change gamma, as you can see here a little bit, gamma is 0.8, you have this much longer nucleation time, but eventually you get rapid nucleation and you populate the system with these small scale vortices, again, all of the same sign. Now, the time that it takes for that to happen is scales something like gamma to the -8. We don't know exactly why that's the case, but that comes from the numerical calculations. So this is the kind of picture what you get in the dense state that you've created at different values of gamma. And as I've already mentioned, as you decrease gamma, this gas of vortices crystallizes into this lattice state. And actually, maybe I'll show you some movies of this. So this is typically what it looks like. Notice that these vortices are shielded vortices. You have one sign of vorticity surrounded by vorticity of the opposite sign. And the net effect of that is that the vorticity outside of these structures is essentially 0. So the circulation goes to 0 in a finite distance from the vortex. So these vortices do not actually advect each other. And that is, you know, if this were a dilute gas, you would have a gas of weakly interacting structures, which is much more amenable to analytical work. So that's the case. Gamma is 0.5. I'll just show you what it looks like in the crystalline state. These vortices have basically more or less a fixed location, and they just wander around a little bit, but they are all rotating, right? They're all rotating. And notice also that the tripolar structure has more or less disappeared. Now you have essentially much more axisymmetric structures in the vortex state. We have not done that. But I'll show you something about the motion of the vortices themselves. And if you can think of one of the vortices as a passive tracer, then you know that will answer at least some of your question. So I'll show you that. So the point is that in some of the experiments that I mentioned at the beginning, you do see these kinds of crystalline vortex structures. And if you look at the trajectories of these vortices, so what we've done is we've taken random vortices and we put them all in the center of the domain just by translating the system, and we trace their motion away from the origin, and you can see here that the vortices are moving around quite a lot, of course, in random directions. In the crystalline state, which is the one on the right, the vortices essentially stuck near their initial location. And if you look at the mean square displacement as a function of time, when gamma is very small, there is no mean square displacement. This blue line is essentially horizontal, but as you increase gamma, you pick up a finite slope at a well-defined gamma. And of course, the slope corresponds to the effective diffusion coefficient. And you can see that the diffusion coefficient is 0 up to this critical value of gamma, and then it becomes non-zero. So that's a signature of a non-equilibrium phase transition. Essentially, you know, if you go in this direction, you go from the crystalline state and the crystal melts. Yeah, it's interesting that this is in fact a random walk. I mean, the slope is, you know, is a half with time. So the vortices, is there a question? No, this is all Brownian motion. The vortices at small gamma are relatively bigger than the ones at larger gamma, and so you can pack more vortices when you have larger gamma. They also become more tripolar, as you can see here. Because the vortices are smaller at larger gamma, as you increase gamma, the number of vortices in this dense gas at large gamma slightly increases, as you can see in this plot here. But perhaps more relevant for our purposes is the circulation as a function of the distance from the center of a vortex, averaged over the vortices, and you see that the circulation builds up, but because of the shield with the opposite vorticity, the circulation actually goes to zero, roughly at length L1, which remember L1 is 2 pi over K1, and that is the largest forcing scale that we force via the instability. So beyond that scale, the vortices do not advect each other. It's very different from the usual kind of point vortex problem where vortices always know about each other. So here's a summary of what we have so far. We have the condensate. We have this condensate containing the small vortices, the vortex gas, and then finally, if you go back down to here from up there, over here we have this crystalline state that I've just talked about. So in the remainder of this talk, or in the second half of this talk, I want to relate this to what you see in 3 dimensions. And maybe that will shed some light on what we really mean by this instability forced turbulence. So there are various ways of trying to see what would happen if you add a 3rd dimension, okay? And so one thing that has been done in experiments is that people study turbulence in a fluid layer, and then they decrease the height of the layer. And then there's a critical height below which you start seeing these large-scale condensates spontaneously appearing on top of the turbulent state. Similar things occur in magnetic fields, strong magnetic fields. The point about that, again, is that the magnetic field introduces anisotropy into the problem. Just like having a thinner and thinner layer, that also makes the turbulence anisotropic. But I'm going to talk about the 3rd case. This is the case of rotating turbulence, convectively driven turbulence, which is also anisotropic, because as you increase the rotation rate, the horizontal scale of the turbulent cells gets smaller and smaller, and so you get structures which are very elongated. And here is an example of what you see from above in an experiment. You see a gas of cyclonic and anticyclonic vortices. If you look at this from the side, this is what you see. You see these columnar structures, very anisotropic flow. Here, the red structures correspond to descending cool liquid. They look red because of the visualization, liquid crystal visualization. And these blue structures are rising hot plumes, actually. This is from an experiment. So I want to understand, how this kind of structure relates to the purely 2-dimensional system that we've been talking about. So I have to tell you a little bit about parameters that are relevant to rotating flows. So bear with me. So here is the parameter plane. So on the vertical axis, this is a log-log plot, is the Rayleigh number. That's a parameter that's used to measure the energy input of the strength of the forcing of the system. And on the horizontal axis is a measure of the rotation rate. Now, if you're below this black line, the conduction state is stable. You have to exceed that black line in order to get convective instability. So this is well known. This goes back to the work of Chandrasekhar, for example. Now, for geophysical and astrophysical flows, you're interested in very large values of the Rayleigh number and very large rotation rates, because the rotation rates here are non-dimensionalized relative to viscosity, okay? So we're interested in numbers like 10 to the 20, right? And if you have equations with numbers like 10 to the 20, they are hard to simulate, as you can imagine. They're extremely stiff problems. But they are the parameters that are relevant to atmospheric dynamics. And so what we really want to do is we want to go into this shaded region, but we want to go as far to the top right as possible. Okay, and that is impossible right now in DNS using direct numerical simulations, also impossible in experiments in the laboratory because the scales are so much smaller. As you can see here, here are some experiments that just barely get into that region at the bottom. Now, the reason we're interested in that region is because that is the region where the rotation is actually important. And the way we measure the importance of the rotation is through something called the convective Rossby number. And that is a measure of a typical velocity, convective velocity relative to the rotation rate omega. But of course, the typical convective velocity is generated by the forcing, and so that depends on the Rayleigh number. And so the Rossby number, the convective Rossby number, is given by this expression in terms of the Rayleigh number and a measure of the rotation, and I'm going to use the Ekman number here, which is 1 over the square root of this Taylor number. Okay, it's defined in this way, but it measures the rotation relative to viscosity. Okay, so that's the parameters. And this heavy dashed line corresponds to a convective Rossby number equal to 1. If you're above that line, you're not affected by rotation. If you're below that line, rotation becomes important, and it becomes significant below this line here, which corresponds to convective Rossby number of 0.01. Okay, so these are the strongly rotationally influenced flows in that shaded region. So how do we study that? Well, here is the usual Navier-Stokes equation. It's been non-dimensionalized with an arbitrary horizontal length scale L and an arbitrary horizontal velocity U. So that introduces that Rossby number we saw on the previous slide. There are some additional non-dimensional parameters, this P, gamma, and a Reynolds number and a Peclet number that are defined over here. So P is a measure of the strength of the pressure. And gamma is the important parameter for our purposes because that measures the strength of the convective driving, the buoyancy forcing of the system. So what would you do with a problem like this? You're interested in very small values of the Rossby number, meaning rapid rotation. And so you have a very large term in the equation, and that has to be balanced by some other large term. And the only other large term is the pressure term. And that balance leads to something that's called a geostrophic balance. And I'll talk about that in a second. But geostrophic balance is not enough. You need to know what is the dynamics on top of this balanced flow. And to get access to that flow, we are going to pick horizontal scales L relative to the vertical scale, which are going to be of order the Rossby number. And I've decided to call the Rossby number epsilon here, just to remind me that I'm looking at low Rossby numbers, rapidly rotating flows. And then we do a multi-scale expansion. We introduce scaled horizontal coordinates in a vertical direction. We have to have a large scale because we're forcing the system over a large height. The scales are small horizontally, but the system is large in the vertical direction. So we have a slow vertical scale, capital Z, and associated with that are different time scales. And you put all that in the equations, and you're looking for solutions where the horizontal velocities are comparable to the vertical velocities. That's because you want to capture convective driving of the system. The temperature is going to be horizontally average temperature plus a departure from that called theta. And we're looking at situations where you have strong buoyancy forcing, so large gamma, large P, and that leading order, then you get this geostrophic balance equation here, where the Coriolis term is balanced by the horizontal pressure gradient. The flow is horizontally divergence-free. That allows you to introduce a stream function, and the stream function turns out, if you go into this first equation, turns out to be simply the pressure. So this is what you see anytime you look at a, oh, okay. Okay. So the stream function is just the pressure. So this is what you see anytime you look at a weather map. You know, if you have a low pressure region, for example, it's not that everything falls directly into that low pressure area, but in fact you get cyclonic motion, right, around, sorry, this way, around the low pressure region. That's exactly what I'm talking about. The flow is going to follow lines of constant pressure, right? So we all know this, but we're interested in the dynamics on top of this balanced flow. And that you can get by going to next order 1, in this expansion in powers of epsilon. And there you get 2 coupled equations, one for the vertical vorticity omega, which is advected horizontally and is strengthened by vertical stretching and is dissipated by viscosity. And then you have an equation for the vertical velocity, which is advected horizontally. This is just the pressure term. Remember, psi is P, but it's driven by buoyancy and there's some dissipation. So this is not closed, but it turns out that for the choice of the horizontal scale L that I made, if you go to yet higher order, then you get an equation for the evolution of this temperature perturbation theta here. So that's advected horizontally. Then there is a contribution from the vertical advection of the mean temperature gradient, some dissipation. And this introduces this mean temperature, and that evolves on a slower time scale due to the divergence of the vertical heat flux and some dissipation. So it's kind of remarkable that these equations close with this choice of the horizontal scale. And if you pick a particular choice for L, which I've chosen to be the Ekman number to the 1/3, that is the linear convective instability scale at large rotation rates, and you pick for U a viscous velocity, then you get an equation, a set of equations that look roughly like Bénard convection. The equations we have for the vertical vorticity, vertical velocity, temperature fluctuation, and then the adjustment of the mean background. Now, these equations are very nice, right? Because there's no small or large parameters in them, at least provided you pick this combination of parameters to be of order 1. So you have a large Rayleigh number, remember 10 to the 20, but you also have a very large rotation rate. That means the Ekman number is very tiny. And I'm saying that the product for the validity of these equations should be of order 1. Notice there's no rotation in this problem, right? That's because the rotation is in the balanced state that was obtained at order 1 over epsilon. The rotation actually reappears at higher order, but those are small terms when Ekman number is small. And we have some boundary conditions. Basically, the top and bottom is impenetrable, stress-free, fixed temperature with larger temperature at the bottom than at the top, right? So those are the boundary conditions. And this is a closed set of equations that is well posed. And as I said, it's much easier to integrate because there are no small or large parameters. Just a couple of comments about this. So what have those equations achieved? They've eliminated Ekman boundary layers at the top and bottom at the boundaries. They've eliminated fast inertial waves. So the only inertial waves that remain are inertial waves whose frequency is comparable to the eddy turnover time. The equations may not look like Navier-Stokes, but I'm going to try to convince you that they are really good equations for studying this problem. In other words, that they capture the phenomena that we see in direct numerical simulations. They are fully 3D, they are fully nonlinear. So this is not a small amplitude expansion or anything like that. This is strongly nonlinear. And they actually have a reflection symmetry, which suggests that in the limit of rapid rotation, the number of cyclonic and anticyclonic vortices should be approximately the same if they are stable. So what do we see when we integrate these equations? Well, here is that combination of Rayleigh and Ekman that we identified in the theory and as a function of the Prandtl number, sigma. And we see that in this region, when you're not forcing strongly, you have cellular convection, kind of the classical convection. But as you increase the forcing, you get this region of Taylor columns you saw in the experiments by Sakai that I showed you. And these columns then break up into plumes that don't penetrate all the way across the layer. So that's this plume regime. And then if you force even more, the plumes generate this state of geostrophic turbulence, which is like turbulence, except that on all active scales, you have geostrophic balance. Okay, so it's a different type of turbulence, if you like, from the standard turbulence. This is what it looks like in, in the snapshots from the simulations. Here, is the Taylor columns, and as I'm increasing the Rayleigh number, the Taylor columns start to break down into this plume regime where plumes emanate from the boundaries but don't go all the way across. Here is the corresponding picture for this value of the, Rayleigh-Ekman to the 4/3 at different values of the Prandtl number. And you can see when you go from high Prandtl number to lower Prandtl number, you go through this plume regime into this geostrophic turbulence regime. I don't have movies of this because these are 3D calculations, and the movies are very memory intensive. But the thing I want to emphasize, the structures that you see in these kinds of flow look like this. So this is actually the temperature, but the vorticity plot would look very similar. You have a core of one sign surrounded by an envelope of the other sign, just like we saw in the two-dimensional problem. This envelope actually extends all the way across, but for visualization reason, the color table was chosen in such a way that you don't see it over here. So these are exactly the type of structures or 3D analogs of the type of structures that we saw in the two-dimensional problem. Yeah, you have like a shield or, right? So you have one sign of vorticity and around it is a shield of the other sign of vorticity. And that means that these structures also interact very weakly because the circulation at large distances from them is essentially zero. These are from the reduced equations, yeah. Now, if you look at the reduced equations and you integrate them for a long time, you see that there is a gradual shift in Nusselt number, and that corresponds to increase in what we call the barotropic energy, kinetic energy. So that's the energy in the two-dimensional mode, right? It's like the average over height, while the three-dimensional fluctuations don't evolve hardly at all. And you see from a top view that as a function of time, you're generating this condensate that we talked about in the 2D case. But now it's in 3D, right? Now it's in 3D. This is what it looks like. You have this coherent turbulent structure, and it's a barotropic structure, and it's embedded in this background of baroclinic small-scale fluctuations. This is what it would look like from the top. You see the formation of the condensate in the system. In terms of spectra, well, there are two types of spectra you have to look at. You can look at the spectra of the barotropic state and of the baroclinic fluctuations, the small-scale three-dimensional fluctuation. So if you look at the 2D, the barotropic spectrum, you see here the entropy cascade, the direct entropy cascade with spectral index -3. That's typical of what happens in 2D. Up here, you see the condensate that also has a spectral index -3. That's due to the large-scale vortices. But the three-dimensional fluctuations, the baroclinic fluctuations, because they are fully three-dimensional and essentially isotropic, they have approximately a Kolmogorov spectrum, k to the -5/3. Now, if you perform a barotropic baroclinic separation, so you take the vertical vorticity and you break into the barotropic part, the 2D part, plus the 3D fluctuations, and the same for the stream function. Then you get a 2D vorticity equation for the barotropic mode with a term that comes from the fluctuation interaction. That is the source term that I was modeling in the first part of the talk through that instability mechanism. So it comes here from the baroclinic interaction. Of course, to determine what that source term is, you have to calculate how the baroclinic fluctuations evolve, and there's a separate equation for that. But we've seen that even with this term present, under some conditions, you can get a condensation in the largest possible scales, even though this is not a 2D problem. I want to emphasize, it's not a 2D problem. Now, what do you see? Well, if you look at the box scale mode and you look at the barotropic energy in that state, you see that it grows initially exponentially, takes off super exponentially here, and then it continues growing, right? So that is the growth of the condensate. The other modes, higher wave numbers saturate, while the baroclinic modes in red hardly change at all as a function of time. So we've tried to validate this against DNS. Of course, DNS have to be done at finite Rossby number or finite Ekman number. Stefan Stellmach did the first calculations of this type. He found the cellular mode. This is the side view. This is the top view. He found these columnar structures we talked about, the plume state and the geostrophic turbulence state. Maybe if you have good eyes, you might even say there is a large-scale vortex appearing there. More recent calculations, these ones by Selin-Gervili, showed again the evolution to large-scale structures in the same regime as our where our model, the reduced equation, should apply. You have the same evolution of the box scale that continues growing while all the higher wave numbers saturate. This is a longer time view of that evolution. So this is the formation of the condensate. The spectral behavior is almost identical. In the baroclinic state, you have this Kolmogorov spectrum. In the barotropic part of the spectrum, that's the 2D part of the spectrum, you have the entropy cascade and the vortex up here. You can also look at what happens if you make your domain anisotropic. So we've changed it from a square to a rectangular domain, and you see that. So this is showing the vertical vorticity, the barotropic vertical vorticity, the barotropic stream function, and you see here the evolution of essentially a Kolmogorov type flow superposed on the turbulent flow. So you have flow up, flow down, flow up, flow down. This is top view. And that is generated by the anisotropy of the domain. And if you do simulations in rectangular domains, you see similar evolution of a turbulent Kolmogorov flow. So that suggests to us that the equations are really capturing the behavior of the system. So in the remaining few minutes of this talk, I'd just like to say a few words about what happens when you go away from the asymptotic regime. So you back off to finite rotation rates, right? So our asymptotic regime really represented infinitely rapid rotation. So we're going to back off to finite rotation. And so here I'm looking at a case which with the rotation is only moderately important. Rossby number is less than 1, but not much less than 1. But what we're going to try to do is we want to see what does the large scale vortex actually do? You know, why is it generated? What's the mechanism? And so what we do is we integrate the full Navier-Stokes now without any large scale vortex, and it persists. No large vortex is created because we're far from low Rossby number, okay? But we can insert a vortex, a large scale vortex into the system as an initial condition. And we characterize that vortex by an amplitude A. And you see that when that amplitude A is large enough, you have initial decay, but then the vortex kind of picks itself up and arranges for the conditions that allow it to be self-sustained. So if the amplitude is too small, then the vortex decays. In fact, it decays more rapidly than viscosity, right? And that's because turbulence enhances dissipation, at least down here. But here, the effect is the opposite, right? The vortex actually generates conditions for itself sustenance. And so here is a picture of what that looks like as a function of time with no vortex on the left and the vortex on the right. So on the left, there's some energy being input via the convective instability, and there's some dissipation. And in steady state, or stationary state, those balance. And so you have no net energy input. That's the black curve, right? So that's the usual turbulent state. But with the vortex, something interesting happens. First of all, you're putting more energy for the same parameter values. You're actually putting more energy into the system. And interestingly enough, your dissipation goes down. It's a surprise, right? Your dissipation is going down. And so if you sum the red and the blue curve, you actually have net energy input into the system, right? So the vortex arranges the conditions for its existence or for its growth. And how does it do that? Yeah, yep. And this is how it does it. So this is the case with no vortex superposed. Here is the large vortex, the large amplitude vortex. And you can see that if you look at the kind of signature of the presence of the vortex, you see it in the fluctuations, right? So this is the small scale fluctuation. That was that source term for the 2D barotropic equation. Here is the rate of working by that term. And you can see very easily that there is a very nice footprint of the presence of the vortex. Essentially what the vortex is doing, it's arranging for the phases of the small scale fluctuation to allow it to take energy directly from small scales into the largest box scale, bypassing the energy cascade, that inverse energy cascade. And you can see that in the appearance of the energy here at small scales in the case where I initialize the system with this large scale vortex. So the last thing I want to mention is a couple of things about things called wall modes, which are present when you do an experiment. Because unfortunately, we can't do experiments in free space. We have to put them in a container. And when you have a container, you have boundaries, you have side walls, right? And it turns out that for these flows, the first mode of instability as you increase the Rayleigh number is actually to a wall confined state. We call these wall modes, and only later does you get bulk convection, bulk turbulence when you cross this Chandrasekhar line over here. Now these wall modes are very interesting. So here is a picture from above. This is the velocity plot. Here is the temperature plot. The system rotates in this direction. These wall modes precess in the retrograde direction along the boundary. And you can see them very nicely in a space-time plot here. But it turns out that even when you exceed that Chandrasekhar threshold for the bulk turbulence, like here, you still see these wall modes. They persist even in the turbulent regime. In fact, they are extremely robust. You can try to block them by putting a boundary like this, and the thing just happily goes around, and nothing changes. The frequency doesn't change, the wave number doesn't change, and you can play with different geometries, and the wall mode just goes around whatever you put there. And the important thing is that it does that even in the presence of the bulk turbulence. Now, this is reminiscent of two-dimensional protected state, topologically protected state in two-dimensional chiral systems, like shown over here. I don't have time to discuss this, but in these situations, you can derive, because they are strictly 2D, you can derive a theory that tells you that you will have robust topologically protected states that survive the presence of these kinds of barriers. And of course, this is important, for conduction properties, say in two-dimensional structures like graphene and so on. It's a big topic right now. But for the experiments that people want to do on geostrophic turbulence, these wall modes are a big problem. And they are a big problem because they carry a lot of heat. They're well organized, they're not turbulent, they carry a lot of heat. And so you'd like to suppress them, but the method I suggested in the previous slide doesn't work because the modes just go around. But here is another proposal. So this is a side view, and we're proposing to put a little barrier here with appropriate boundary conditions, or maybe we just kill the flow in this region, which you can do if you have a finite element code. And you can study the effect of that barrier on the generation of these wall modes. And this is what you find. So here is an annulus, periodic boundary conditions in this direction. This is the homogeneous case where you also are periodic in this direction. And so this is the turbulent state like you would see in the bulk. That's the geostrophic turbulence. If you have lateral boundaries here, you have these wall modes, even in the turbulent regime. This, if it's rotating in the counterclockwise direction, this mode is going to travel in this direction. This mode is going to travel in the opposite direction. And they really mess up the heat because this is the Nusselt number, the heat flux transported by the system in that bounded domain. It's much higher than the Nusselt number in this region, which is the homogeneous or bulk convective turbulence. But with our fins that we embed in the boundary, and that their width is very tiny. It's Ekman to the 1/3, that's enough, because the width of the wall modes is Ekman to the 1/3. That's the dashed lines. You get a state that looks essentially indistinguishable from here. And if you have just one fin, you're already close to the homogeneous Nusselt number. You put two fins equally separated, you actually go below the background homogeneous state. Because of course you're excluding some of the volume now, so you have. Yeah, in here, these fins kill these wall modes that you see prominently here, and the state inside here is, I argue, is statistically identical to the bulk state with purely boundary conditions. I did exactly this. I did this, and instead of having a finite bump, I just had a flake, a very thin flake, and it's just a horizontal boundary. So go here like this, right? Is it clear? I'm basically just taking this thing for that particular calculation. I'm just shrinking it down. Tiny horizontal flake, and that's enough to kill the wall mode. And it has a huge effect on the Nusselt number. And that's important for people who try to study geostrophic turbulence in the laboratory, because as you can see, if you don't do that, your behavior is going to be contaminated by these wall modes. So I'm finished. So the conclusions are very simple, that highly anisotropic systems favor formation of large-scale structures. They can be these large-scale vortices, like in these condensates, or it could be jets, for example, like in the anisotropic domain. The important thing is that this happens in 3D, right? It happens in 3D. And of course, we are interested in the formation of these large-scale structures and the propensity to form large-scale structures, because of course, that's what you see in the atmosphere and in the oceans. And we think that the fundamental physical reason for that is that you have a thin layer. So you're far from having isotropic three-dimensional turbulence. So that's all. Thank you for listening.
Well, thank you very much. Very interesting talk. Is there any question? Well, I have one myself. So let's see if I've understood. So summing up. So you have this 2D rotation, so like a convection and rotation in the 3D problem, and that somehow effectively reproduce the model that you did at the beginning?
Well, I have for that particular problem, I have an expression for the source term, that would be driving, the two-dimensional version that I started off with. And some of the structures we see in 3D are very similar to what we found in this 2D problem.
But no way to derive something from the 3D, something similar to the model you proposed at the beginning?
We don't have a way of, what people have done is that, they've done simulations of layers of different thickness, but there is no analysis that generates the kind of reduced equations in that situation that would be analogous to what I did for the rapid rotation case.
Exactly. Okay.
So,
that looks complicated.
Yeah. So not everything is understood. I'm not pretending.
No. Very nice. Very nice. Yeah, sure. Yeah, shower.
How this high is related to the larger distance? They are related or not? you can characterize them in some and because of parameters. It should be small.
Mhm.
And then you have large scale structure. It's not a large.
Mhm.
This large one for the small parameters, one of the parameters is some power.
I'm not completely clear what you want to know about the large scale structure. So let me. A highly anisotropic system means that the turbulent state is far from fully three-dimensional isotropic turbulence. So one way to do that is by, for example, introducing rotation, where rotation favors small scales in the horizontal, but doesn't do anything to vertical scales. Okay, so the scales are anisotropic. So that's one way to do this. Or in the case where you have a thin layer, as you vary the depth, that is another way of making the system anisotropic, because you're not allowing all the scales in the vertical, right? Because the system has to fit in the layer. So there are different ways of making the system anisotropic. There is some number, and so the large scale of well, so you have to tell me what you want to know. If you want to know what is the ratio of scales, for example, in rotating convection, then the horizontal scales are order Ekman to the 1/3. The vertical scale is of order 1. The ratio of the scales. I'm
trying to say if the size of the vortex is related to the anisotropic. That's why the size of the vortex into the
large scale vortex. Oh, that has to do with the domain size. That's just the domain size.
Not the vertical direction.
No.
Not the anisotropic parameter.
No, the large scale vortex, the condensate is just the domain size. The energy is going to cascade to the smallest available scale to the level of anisotropic. Yeah. Provided the system is sufficiently anisotropic. Well, in the rotating case, it's the Ekman number. And I said that the ratio of the scales is Ekman number to the 1/3. And so I need Ekman to the 1/3 to be substantially small compared to 1. Okay, so that gives you a range, you give me a viscosity, you give me a length scale, I can tell you what is the rotation rate, for example. You understand? So let's say Ekman to the 1/3 is something like, well, typically 10 to the -2 is what people can achieve, in direct numerical simulations, because that corresponds to Ekman number of 10 to the -6, which is more or less what people can do. And there you already see the formation of the large scale structures. I showed you pictures of that. So Ekman to the 1/3, of order 10 to the -2 or smaller is certainly enough. But whether there is a hard, critical value, that is very unlikely, right? So you can quantify this.
One more short question, and we finished. I was interested in the vortices you showed at the very beginning. Mm-hmm. So this is small vortices and then you show more. So and you said, but you didn't elaborate much about this phase transition where you get that only vortices of one side. Mm-hmm. So and you
so
you put so you are forcing it, so the vorticity is not conserved, of course, because you are forcing, I guess.
Oh no, vorticity is not conserved, of course.
Now you will not have that, I guess. So you're forcing randomly, then one vorticity is selected.
Yeah, and it could be either vorticity, right? So either the positive vortices are destroyed, or eventually, or all the negative ones are destroyed eventually. So it's like the Ising model or something.
And that's well understood in this model.
No, because this is a non-equilibrium problem. This is not classical equilibrium phase transitions.
Okay.
Right. This is a driven dissipative system. But it behaves, I mean, we haven't been able to look at what happens to growth of correlations, for example. That's the classical way of trying to understand approach to Yeah, in this case, it's discontinuous. Yeah. Yeah, it's a first order, so-called first order transition. But that again is terminology, you know, from equilibrium phase transition. So.
Let's thank Edgar once more. And thank you for coming.